This is not a bridge. Not yet. It is a rectangle of material, smeared evenly across a design domain, with a single weight hanging from one corner. Watch what a computer does with it. Material starts pulling toward where the forces flow. Members appear. Voids open. A truss begins to resolve out of the gray. And it keeps sharpening, every step provably stiffer. After 146 iterations it stops. Nobody drew this. The computer discovered it by doing nothing but obeying the equations of stiffness. That process is called topology optimization, and today we build it from scratch. No black box. Every line verified against physics. The goal in one sentence: distribute a fixed amount of material in a fixed box so the structure is as stiff as possible under a given load. A box, held at some supports, with a load pushing on it. Which parts should be solid, and which should be empty? We measure stiffness with compliance, C equals U transpose KU, the work the load does on the structure. Small compliance means a stiff structure, so we minimize it. Subject to two things: the structure must actually obey the physics, KU equals F, and we can only use so much material. Every little element in the box gets one number, a density between 0 for void and 1 for solid. 19,000 of them for the big runs. The optimizer's whole job is to choose them. There is a catch. A density of 0.5 half-gray is not manufacturable. We need the answer to come out black and white. The trick that does this is called SIMP. The stiffness of an element is its density raised to a power p. That tiny emin keeps a fully void element from making the maths blow up. It is 9 orders of magnitude below solid, far too small to change any design. Here is why the power matters. At p equals 1, stiffness is linear. A half-dense element costs half your budget and buys half the stiffness. Gray is a perfectly fair deal, so the optimizer happily leaves a smeared cloud you can never build. At p equals 3, that same half-dense element still costs half your budget, but now buys only 0.5 cubed, 12.5% of the stiffness. Gray has become a terrible deal, 4 times worse. So the optimizer discovers on its own that solid or empty is always the better spend. Penalization does not force black and white. It makes black and white the economical choice. To improve the design, the optimizer needs the gradient, how compliance changes if it nudges each element. With 19,000 elements, computing that the naive way means 19,000 solves. That would be hopeless. It turns out you need exactly one. Differentiate compliance, remembering the displacement U itself depends on the design. You get 2 terms, one of them involving that expensive derivative of U. But differentiate the physics equation KU equals F, and you can substitute that expensive term away entirely. The 2 U transpose K terms cancel, and the whole gradient collapses to a single clean expression. The adjoint problem turns out to be the problem you already solved. The structure is self-adjoint, so there is nothing new to compute. Element by element, the gradient is just the strain energy stored in that element. And it is negative for every element. Always adding material can never make a structure less stiff. The test suite asserts that on every run. Now a problem that nearly every first attempt hits. Run the optimizer with everything we have so far, and this is what comes out. Those alternating solid and void squares are a checkerboard. And here is the trap. This design reports a lower compliance than the clean one, 203 versus 239. On paper it looks stiffer. In metal it is worthless. The checkerboard is not noise and not a bug. It is a flaw in the finite element model itself. The simple square elements report a checkerboard as artificially stiff. The optimizer is faithfully chasing a reward the discretization invented. The fix is a filter, and once it is on, the same problem resolves into honest, connected members. It reports a higher compliance, because that number is finally telling the truth. Measured, the checkerboard pattern drops by a factor of 9. The filter is simple. It blurs each element's density with its neighbors inside a radius Rmin, so any pattern finer than that radius simply cannot exist anymore. Build a weight matrix once, then let the physics see a filtered density field. Dividing by the row sums makes it a true average, so a constant field maps to itself and the boundary is not eroded. Because it is an exact change of variables, the chain rule gives an exact gradient, one a finite difference check can verify to 11 decimal places. And this buys something important. Because Rmin is a real length, not a number of elements, refining the mesh does not change the answer. Coarse and fine, at the same physical radius, return the same structure. 99.1% correlated. Without the filter, a finer mesh would just grow finer and finer members forever. The mesh dependence the filter exists to kill. With an exact gradient in hand, how do we update the densities? The classic answer is the optimality criteria update. Push material toward the elements with the highest strain energy, while holding the volume exactly on budget. The volume is enforced by a single multiplier lambda, found by bisection. Guess lambda, apply the update, check the volume, repeat until it lands. And here the repo turns up something worth reporting. Textbooks often say OC is not a true descent method, compliance sometimes ticks upward. But measured carefully, that non-monotonicity comes entirely from stopping the bisection too early. Tighten it, and across 4 different problems the compliance never once increases. The extra steps are pure arithmetic, no solve, so it costs nothing. Now every piece is in place, the SIMP law, the self-adjoint gradient, the filter, the OC update. Let them run together and watch the structure resolve, the same clip from the open, but now you know exactly what each frame is doing. The gradient pulls density toward the load path. SIMP makes the in-between values unprofitable. The filter holds every member above the minimum length scale, no checkerboard forms. The OC update moves material each step, volume pinned exactly on budget, compliance dropping monotonically. The members thicken where strain energy is high and vanish where it is not. Converged. Compliance 233.7 in 146 iterations, a number this repo generated and locked, not quoted from a paper. Topology optimization is often shown as magic structures that appear from nowhere. It is not magic. It is 4 ideas you can each check. Penalize gray so the answer is manufacturable. Get all 19,000 sensitivities from one solve, because the structure is self-adjoint. Filter to remove the model's invented reward and fix a real length scale. An update with optimality criteria, volume held exactly. And the reason to trust this particular build, every physics claim has a test, and every test prints the number it measured. The element matrix, the gradient, the filter, the whole optimizer each gated before the next was written. That is what no black box actually means.